Okay, I took a look at the upcoming question, and my answer ended up a little bit off. I tracked down why. It looks like it's a significant figure thing. This is one of the few times where the online system, the way that it does it, we're losing track of some significant figures if you follow my regular instructions. So in this case, in the upcoming problem, I solve at one point for 11.4. I mentioned offhand that to higher significant figures, it's 11.443. For this upcoming problem, for the online homework, go ahead and take it to 4 or 5 significant figures with any of the stuff you're dealing with, and that should bypass the problem. Okay? I went back and I double checked it, and if I had used 11.44, then I would have gotten exactly the answer. The answer that you end up seeing is technically a little over 2% off, so the online homework system wouldn't accept my answer. I'm going ahead and giving you that warning now. I apologize for the confusion on that. Up to this point, as long as you use the 3 significant figures, we haven't run into any problems. You're also welcome to use 4 if you'd like. I never said that you can't. I just said that 3 is usually the ballpark we look for. Okay? Okay, so today we're going to take a look at some of the other problems that we have on the new Quest homework. So I've got a few of them laid out. This will be the first one that we take a look at. It's a 2-part question. So it says a block weighing 9.7 newtons requires a force of 3.9 newtons to push it along at constant velocity. Now, there are a few things that are a little bit different about this, but like usual, let's start off by drawing a picture. Now, normally, when we describe how heavy something is, what a lot of you are prepared or most used to is, well, what you're really used to is talking in pounds. Pound is a unit of force, which means it's most similar to newtons. So what they're saying is, depending on how you interpret it, with this being my object, here's a free body diagram. We're going to look at the forces acting on it. I've got a force of gravity downward. We're near the surface of the Earth. I've got a normal force upward. And what they're telling us, I presume from their notation, is that the force of gravity is 9.7 newtons. Now, we're familiar, hopefully at this point, with finding the force of gravity. We know near the surface of the Earth that Fg equals the mass of the object in kilograms times the acceleration due to gravity, which is positive 9.81 meters per second squared. Remember, whenever I use the notation of g, I always use positive 9.81, because we'll keep track of direction later. I'm going to skip ahead a little bit on this because it's more in keeping with my interpretation of the word weight. As we've probably talked about in class, or will talk about in class, I determine weight to be the actual normal force supporting you. That is why when you deal with the astronauts in the International Space Station, we call them weightless. They are actually without weight. There's no normal force required to hold them up. There is very much a force of gravity on them. Now, if you're watching this a bit before we cover it in class, or need to brush up on it, don't worry about that too much. We take a look at the circular motion stuff that we've got and universal gravitation. It turns out that while the astronauts do have a force of gravity on them, we normally call them weightless. They don't actually have a normal force acting on them. And that's as a result of them moving in what we approximate to be circular motion. All right, enough of the sidetrack. In short, some questions, and sometimes the AP exam as well, among other things, will refer to the weight of an object in newtons, and they're talking about the force. Usually they're talking about the force of gravity pulling it down, but we have a block here that is sitting on a table, and while it is moving at a constant velocity, moving, I'm going to assume, to the right. I can draw this however I'd like. We don't have it falling through the table, we don't have it jumping up off the table, so when you do your sum of forces in the y direction, that's going to be equal to the normal force minus the force of gravity. Here's the minus, that's why we use a positive 9.81, because I keep track of the direction when I apply Newton's second law, equals my mass times my acceleration in the y, but this thing is not jumping up off the table, nor is it sinking down into it, so this equals 0. We will find that the normal force will be equal and opposite to the force of gravity. Once again, While they happen to be equal and opposite, this is not an example of a Newton's third law pair. This is not what Newton's third law is talking about, and these are most emphatically not Newton's third law pairs. They happen to be equal and opposite because the forces are balanced in the y direction. This is a result of Newton's second law, not the third law. All right, that was a lot of additional information, but this question, while I really like it, uses some terminology that I don't focus on in class, so I wanted to spend a little bit more time. Now we can go through and we can find the mass of this object. It looks like it's going to be slightly less than 1 kilogram with my numbers, because I would then take 9.7 newtons equals the mass times 9.81, divide 9.81, I would get the mass in kilograms. Now an important distinction in this, the mass is always whatever the mass is. I can take that object, I can take it to the moon, where it would weigh less, but it would still have the same mass. Or I could have it out in deep space where there's no force of gravity whatsoever, but it would still have the same mass. However, this question does not actually ask us for the mass, so we don't have to go looking for it. Here's where we start incorporating what they are looking for, because they want the coefficient of friction. I apologize if I didn't say that. But we have a block that we're pushing along a rough surface, and we are pushing it at a constant velocity, and we are pushing with a force of 3.9 newtons. I could call that F sub P for force of push, or F sub A for force applied. Force applied is usually the more common notation. It is a normal force, it's a physical contact force, but we're going to give it a slightly different name so we don't confuse them. Now, this thing is not accelerating, so if I'm pushing it to the right, something must also be affecting it to the left, and it turns out that we have the force of friction. In this case, it'll be kinetic friction. If I apply Newton's second law in the x direction, I'm going to have how hard I push minus the force of friction, minus because it's to the left, equals my mass of my object times my acceleration in the x. But since we are pushing at a constant velocity, this guy is 0, and we end up with this whole side going to 0. We end up with the applied force, which we said was 3.9 newtons, minus the force of friction, equals 0 newtons. I add the force of friction over there, and I find that my force of friction is equal to 3.9 newtons. Now, if I'm not mistaken, we actually had a quiz in class related to this. I forgot, the bells still work, even when school is not in session. So, moving on. Now we know the force of friction, and they gave us information to find the normal force. We've applied Newton's second law in both of the directions. We want the coefficient of friction. And this was me possibly working a little bit ahead. At the beginning, if we're looking for the coefficient of friction, there's really only one equation that you all have right now to work with. We have the force of friction equals the coefficient of friction times the normal force. Now, I remind you, we used this in the lab where we were pulling the boxes, and we found that the slope, when you graphed the force of friction, or what I had you graph was the pull force, versus the normal force, which, if you take a look at this, is exactly how we got that. We found the slope actually happened to be our coefficient of friction, and it describes the roughness of a surface. Well, now this is the equation that we'll be using. We have the force of friction, and we have the normal force, so we can simply plug these in. We've got 3.9 newtons equals my coefficient of kinetic friction, technically, but it's the coefficient of friction, times my normal force, 9.7 newtons. Now, remember, the normal force in this equation deals with how hard the surfaces are being pushed together. Not me pushing on the object, but how hard the surfaces are being pushed together. That's this normal force. I'm applying a force this way, but that's not squishing the surfaces together. All right, we're almost done. I solve for the coefficient of friction by dividing both sides by 9.7. So we end up with 3.9 newtons divided by 9.7 newtons. You'll notice that the newtons cancel out, leaving us with no units whatsoever, which is exactly what we expect for the coefficient of friction. So 3.9 divided by 9.7. .402. I'm checking my answer key. 0.402062. So they take it to 6 significant figures. Nuts to that. 3 is plenty good for us. So 0.402. This is the correct answer. All right. Now, let's move on to the next part. Because they ask a follow-up question. A weight, W, is now placed on the block and 4.6 newtons is needed to push them both at a constant velocity. What is the weight of the block? Answer in newtons, I believe it's asking for. Okay, so if it hurts to draw a picture, I have the same block that we had before, and now I've put another block marked W on it. Now here's where we're going to want to draw our free body diagram. Again, we've changed things. I've got the following. I still have the force of gravity pulling down on the first block that I'm looking at. There are 2 ways to go about this problem. I'm going to show you the more rigorous one, and then we'll talk about one final thing at the end. We still have the normal force that we had before, and we know that both of these, we'd already been given, were 9.7 newtons. I'm sorry. Let me rewrite that. All right. Because we have things that have changed a little bit. We know that the force of gravity on the block is 9.7. Turns out if you use my interpretation for the weight, we have increased it a little bit. We do indeed have the normal force from the table holding the block up, except this time we now have an additional force in the Y, which I'm going to call W. It's another normal force, but it's the force of gravity pulling on this block and this block having to support it. So if I were to draw a free body diagram of block 2 with W, we have its weight, force of gravity on block W, and we have the normal force from block 1. Well, it should be equal and opposite to this one, and W is actually what we're going to be looking for. I could go into this a little bit more, but take a minute. Take a minute and run through it. In short, let's say that this guy had a force of gravity pulling on it of 3 newtons. It's not falling down into the block and it's not jumping off of it. So like we saw before, its sum of forces in the Y is going to be equal to 0, which means if we have 3 down, it must have 3 up. Here is where Newton's third law pair comes into play. The force downward from this block onto this block must be equal and opposite to the force of this on that. So if this block is holding W up with 3 newtons, then W must be applying 3 newtons downward. I'm simply going to call that W, but it is the normal force from this block pushing down on this block. And that is equal and opposite, a Newton's third law pair, with this block holding the other block up. It's the same as the example I gave in class when I said if you had a blindfold and I put a book on your hand, would you know when the book was there? You would, because it pushes down on your hand as you push up to hold the book. All right, going forward, we still have, actually we've changed things a little bit. I am now applying a force of, let's see, 4.6 newtons. And there is a force of kinetic friction. All right. So here's where we take the information that we learned in part 1. We also know that the coefficient of friction is 0.402. Okay, so when I apply my Newton's second law in the x direction, I end up with 4.6 newtons, my applied force, minus the force of kinetic friction equals 0 newtons, because we'd have the mass times the acceleration. They tell us, while they put this extra block on there and we now push harder, they still say that it is being pushed at a constant velocity, So we're pushing harder to keep the heavier object moving at a constant velocity. The constant velocity tells us our acceleration is 0, and that's how I set this up. We now know that the force of friction is equal to 4.6 newtons in our new case. And we also know that that is equal to mu sub k times our new normal force. Okay, so mu sub k is 0.4. So I've got 4.6 newtons equals 0.402 times my new normal force. I divide both sides by 0.4. I'm going to get that my normal force is equal to 4.6 divided by 0.402, 11.4 newtons. 11.443 if you want a little bit more, but 11.4 should be fine. This is the new normal force that is supporting both blocks, but it's the normal force between the lower block and the ground. So this is an accurate free body diagram. We now know the normal force because that's what's pushing these two together. So I'm going to apply Newton's second law in the y direction. Sum of forces in the y equals my normal force minus the normal force from the upper block, block W, pushing down, minus the force of gravity. Now both of these are minus because both of those forces on this block are downward. Here's gravity pulling down, and we also have this guy, the top block, pushing down on the bottom block, pushing down. So these two forces together, and the normal force from the ground holding all of this up, are the forces acting on it. It will be equal to the mass times the acceleration in the y. We could, as we've talked about before, know the mass. In my case, it's a little bit less than 1 kilogram, but it does not matter because, once again, the block is not sinking into the ground and it is not jumping up off of it. So I now find my normal force. My normal force minus W minus the force of gravity equals 0. W is actually what we're looking for. It should be the weight of the block, or at least it will be equal to the weight of the block from the Newton's second law that we talked about over here with that free body diagram. So it will be equal to the weight of the block. It is, in fact, what we're looking for. So if I know that my normal force in this new setup, we found that just a moment ago, is 11.4 newtons minus W minus, the first block didn't change how heavy it was, so it is still 9.7 newtons, equals 0 newtons. I add W over to the other side, and I will find that W is equal to 11.4 minus 9.7. We end up with about 1.70 newtons. Let me see. Survey says they've got 1.74. Hopefully that's not going to cause any issues with significant figures, but that should be how we go about doing it. 1.74 minus 1.7 divided by 1.74. That might actually run into an issue with the solutions on there. If you're running into problems with this one, come talk to me in class, but this is how you end up doing it. Let's see, 4.6, is there anything that I've got thrown off? Okay. But this should be the solution that you get.